We are solving question 35 of GATE 2012 chemical engineering paper. The question is, in a counterflow double pipe heat exchanger, oil is cooled from 90 to 40 degrees Celsius by water, which enters the inner tube at 10 degrees Celsius. The radius of the inner tube is 3 cm and its length is 5 meter. Neglecting the wall resistance, the overall heat transfer coefficient based on the inner radius in kilowatt per meter square Kelvin is dash. And we have been given the mass flow rate and heat capacity of both the oil and water. Now, here we have been given a double pipe heat exchanger, and we are having the counter flow. So let's just consider oil enters the tube side from here, and the inlet temperature is 90 degrees Celsius and the outlet temperature we have been given as 40 degrees Celsius. Mass flow rate is 2 kg per second and Cp is 2.1. This will be the flow direction, and the water will enter in the opposite direction in the outer tube, and the inlet temperature we have been given as 10 degrees Celsius. Outlet temperature, the out water we haven't been given, and we have been given mass flow rate as 1, CPS 4.2. Now if we draw the temperature profile along the length of this double pipe heat exchanger, we can draw it as, for this oil, temperature decreases from 90 to 40 in this direction. Similarly for water, the temperature will rise from 10 degrees Celsius to some value, that is T naught of water, the output of water. Now the energy exchange between this hot fluid, that is oil and water, we can equate to find this outlet temperature of the water. That is, we can write delta Q of water is equal to delta Q of oil, that is m dot Cp is equal to m dot Cp delta T. This is for oil, this is for water. For water we have been given the mass flow rate as 1, Cp we have been given as 4.2, delta T will be the outlet minus inner temperature, inside temperature was 10 degree. Similarly for oil we can write it as 1 into 2 into 2.1 into temperature difference, in this case is 50, that is 90 minus 40. That is, we can write this as T minus 10 is equal to 50, and this T outlet of our water will be 50 plus 10, that is 60 degrees Celsius. So here this is 60 degrees Celsius and inlet was 10. So at the exit of the heat exchanger, the temperature difference is delta T2 is equal to 40 minus 10, it will become 30 degrees Celsius, and at the inlet it will become delta T1 is equal to 90 minus 60, that is 30 degrees Celsius. Now usually we will be using this log mean temperature difference to calculate the temperature difference due to which this heat exchange occurs, but in this case, since delta T1 is equal to delta T2, the log mean temperature difference we can write it as either delta T1 or delta T2, so that is equal to 30 degrees Celsius. So this we can use to calculate the overall heat transfer coefficient based on the inner radius. So that is, we can write Q is equal to Hi Ai into delta T is equal to m Cp delta T. Now this should be log mean temperature difference, but for our case this will be 30 degrees Celsius. So this we can consider either for oil or for water, whatever we want. So let's just consider this for oil. That is, we can write Hi is equal to, area will be 2 pi RL, that is 2 into pi to the radius of the pipe we have in inner tube is 33 centimeter. That is 3 into 10 raised to minus 2 meter into length we have been given as 5 meter. 5 into delta T will be 30 degrees Celsius from the earlier slide. Mass flow rate of the oil was 2, Cp was 2.1 and delta T was 90 minus 40, that is 50 degrees Celsius. So from here we can get this HIS 210 upon that is we can write 6 pi 10 raised to minus 2 into 150. So you can equate this and we will get the value of HIS 7.43. The units will be kilowatt per meter square Kelvin. So the final answer from the given options, we will select it as 7.43 kilowatt per meter square Kelvin, that is option B.